Welcome to the second part of ENB458 and ENN580. The second part is about digital control, and this third lecture in the second part is about the Z-plane. I'm Peter Cork. Firstly, let's recap what we did in the last lecture. So we've talked a bit about how we can compute a compensator. You've learned previously about how you can design a compensator for a plant using networks of resistors and capacitors. You design it in the S-plane, you implement it with op-amps, resistors, capacitors, or other sorts of discrete electronic components. But it's just a function, and we've talked about how we might be able to compute that. And previous lecture we talked about how we can convert a function which is described in the S-plane in terms of the variable s in terms of a difference equation which we can implement in a computer. So here's an example of a simple compensator, s plus 4 over s plus 20, and we can implement that as a difference equation. The output at time k is a function of the output at the previous time step. We call that yk minus 1. And it's a function of the input, and it's a function of the input at the previous time step. So we can boil down that network, that compensator, into almost a single line of code in whatever language you might choose to write that code in. We also talked about different ways of discretizing a system, and we've come up with a number of substitutions. The simplest one we came up in the first lecture is what's called the backward difference. We simply substitute s as 1 minus z to the minus 1 divided by delta t. And z to the minus 1, you'll recall, is the backward shift operator. It's an operator that delays a signal by a single time step. We looked at this in its inverse form, the backward difference, and we considered it as a simple rectangular integration. We then came up with a more sophisticated integration, which is a trapezoidal integrator, and then we inverted that to get a more precise differentiator, and that's what's called the Tustin transform or the bilinear transform, and that's given here, 1 minus z minus 1 over 1 plus z to the minus 1. We also discussed the Z-transform approach, where you look up an expression that's described in the S-plane, in the Laplace domain, and transform it to the Z domain. And we also talked about a technique called pole-zero mapping, where we take each pole and zero in the S-plane, map them through the exponential to obtain a set of poles and zeros in the Z-plane. And we'll talk more about this mapping between this S-plane and the Z-plane in this lecture. And also in this lecture, we're going to bring this home and actually start to design compensators using this Z-transform technique, which is critical to discrete time control. As I just mentioned, we introduced in the last lecture this shift operator. Z to the minus 1 delays a signal. So what we used to write as a difference equation, we can write that now as polynomials in z to the minus 1. So z multiplying a signal by z to the minus 1 delays it by 1 time step. Z to the minus 2 delays it by 2 time steps. When we perform this transformation from a difference equation to the z transform, we use uppercase letters to indicate the Z transform signal. So we've got capital Y here is the Z transform of Y subscript k, the kth element of the numerical sequence of Y values. Here we've rearranged this into a transfer function form, and this is the Tustin transform that I mentioned just a moment ago. We talked in the first lecture about a simple number sequence, the so-called Fibbonaci sequence, and that could be represented by the difference equation. F at time k is equal to f at the previous time step and the time step before that. It's a simple difference equation. Each number is equal to the sum of the two numbers that precede it. Now we can represent this in a block diagram form. Fk is the output of this system. We delay that by 1 time step to get fk minus 1, delay it again, and we can have f to the k minus 2. If we add those two numbers together, we've got our output signal fk. So if you were to build this circuit, this piece of logic, it would just spit out Fibonacci numbers forever. Now we can generalize this arrangement of delay blocks and coefficient blocks and adding blocks. And if we represent a transfer function in the very general form that's shown up the top there, where each of the numerator and the denominator is a polynomial in z to the minus 1, then we can represent that as a block diagram as shown at the bottom here. We have a long chain of adding blocks through the middle. We have a cascade of delays from the input signal. So the input UK is delayed by 1, by 2, by 3. And similarly with the outputs that we've computed, we delay them and feed them back. And this general block diagram structure can implement that polynomial shown at the top there. Another technique for converting a system from the S-plane, from the Laplace domain into the Z domain, is to look up the S-plane expressions in a table of Z transforms. So here's a little snippet from the PDF document that I've made available via Blackboard. The second column lists transfer functions expressed in terms of the Laplace variable S, and their equivalent is there in the Z-plane in the fourth column. So this is yet another way of transforming from the S-plane to the Z-plane. Now, it's not just a matter of looking these up in the table. These things can be derived. They weren't just handed down on some kind of stone tablet. These can be derived quite easily, certainly for the simple cases. So what we're going to do now is a couple of examples and derive some of these. All right, just to recap what the Z transform does is it converts a sequence of numbers, E0, E1, E2, all the way up to infinity, and the general element we refer to as EK. So the Z transform converts this sequence into a geometric series. So I use the curly Z to indicate the Z transform of the sequence EK. Now, it is equal to the summation from negative infinity to positive infinity of EK multiplied by Z to the minus K. Now, this is called the bilateral form of the Z transform. It's because K goes from minus infinity to plus infinity. Sometimes you'll see it written in what's called the unilateral form, where the subscripts go from 0 to infinity. So this is the general form of the Z transform. All we need to evaluate any of those Z transforms that are in that table is this expression, this summation of EK times Z to the minus K, and a little bit of algebraic trickery. Okay, so we'll consider this particular case. This is a really useful function. This is the step function called the unit step. Sometimes it's called the Heaviside function. And it's defined by this very simple rule. If K is less than 0, EK is 0, and if K is greater than or equal to 0, EK is equal to 1. So here's our general expression for the Z transform. So let's substitute in the values of EK, and life immediately gets quite a bit simpler. The fact that EK is 0 when K is less than 0 means that we can change the start of the summation from negative infinity to 0, because all of the things between 0 and negative infinity are 0. Adding them up, the result is going to be 0. So all we're left with now is the summation from 0 to infinity of Z to the minus K. This is a geometric series, and the solution for the geometric series is well known. I'll put it here, this handy identity. So the general expression for an arithmetic series looks like this. So we can plug those numbers in here. In this particular case, R in our handy identity is equal to Z to the minus 1. So we substitute that into the identity. So we have 1 over 1 minus Z to the minus 1. Multiply the top and the bottom by Z, and we have this result, Z over Z minus 1. So the Z transform of a unit step is Z over Z minus 1. And if we go back and look at the Z transform table, you'll see that that's exactly the entry in the Z transform table. So we've been able to derive one of those. Now let's consider something a little bit more complicated, but equally useful. As we've talked about before, the solution for a system of differential equations is a mixture of exponential functions. So let's evaluate the Z transform of an exponential. In this case, we're going to consider that the exponential has got a value of 0 when K is less than 0. We're only interested in its value from time, from K 0 onwards. and the value of the exponential for each of the time steps is e to the minus akt, because time is going up in discrete steps. It's going up in steps of t, and so time is equal to t, 2t, 3t, 4t. We represent that generally as k capital T, where t is the sampling interval. So this is the definition of the numeric sequence, which is the result of our exponential sampled at discrete time steps. Here is our definition of the Z transform. So we substitute E into this. Keep in mind this handy identity again. And if we do this, we rearrange what's inside our summation into the form of something to the power of k, so that matches the handy identity. Note that we've changed the bottom summation again, so it starts at 0, not negative infinity. We plug what we have raised to the power of k, that would be equal to r in a handy identity. Plug that into the identity, we get an expression like this. We multiply top and bottom by z, and we have the form z over z minus e to the minus at. Look that up in the Z transform table, and that's exactly the result that you will see. So we've derived another Z transform. Now I'm going to set a little exercise for you, and I'm going to get you to determine the Z transform of a ramp. So in this case, the number sequence, starting again from time step 0, goes up linearly with time. So the value of it is equal to k times t, where t is the sample interval. So you're going to follow exactly the same procedure that we did before, and this summation here will be handy. So go to it, and we'll compare notes in just a moment. Okay, here's my solution. So here is the number sequence at the top, and here's the general form of the Z transform, into which I have substituted the kt, which is E subscript k, multiplied by z to the minus k. Now, here's our handy identity. So what I've done is rearranged it into the form of the handy identity. So a is basically a constant scaling factor, that's the t term, multiplied by k, multiplied by something to the power of k. So what I've done is a little bit of manipulation there. Plug A and R into the identity, and I get a result that looks like this. Multiply through top and bottom by z squared this time, and I get the expression given there at the end. If you look this up in your Z transform table, you should see an exact match. So these Z transform entries, there's nothing scary about them. They're not handed down on a stone tablet. You can derive them pretty easily. Some of them are more complex than others, but you've seen we've done 3, and they're really not too challenging. In the last tutorial, I set what turned out to be probably quite a time-consuming problem, and that was to convert this particular transfer function from the S-plane into the Z domain using 4 different discretization techniques: the backward transform, the Tustin transform, the Z transform, and pole zero mapping. It's also called matched transform. So what I want to do is to revisit this tutorial problem, and I'm going to spend quite a bit of time on this now. So just to recap, this particular transfer function in the S domain, in the Laplace domain, if we consider it in terms of the S-plane itself, we can plot the zeros and the poles. And here they are. This is a very simple plot that I generated with MATLAB that shows the 0, which is at S equals -1, and we see 2 poles. We see a pole at -2 and a pole at -3. We obtain the 0 by setting the numerator equal to 0 and solving it, and we determine the poles by setting the denominator equal to 0 and solving for S. So this system has got 2 poles and it's got 1 0. So what I want to do now is just a bit of a recap about the S-plane. Hopefully this is stuff that you know well, but I want to just point out a few interesting areas of the S-plane and their characteristics, because what we're going to do is we're going to map or warp the S-plane into another plane, which is called the Z-plane. It's pretty interesting warping or mapping, but before we do that, I just want to reiterate some characteristics of the S-plane. So in particular, the S-plane, everything that's on the right-hand side of the vertical axis is the region where poles are unstable. So if you place poles there, your system is going to have a solution which diverges. It gets bigger over time. So that's not a good place to put the closed loop pole of a system. If you have got open loop poles over there, if your plant has got poles in the right hand plane in that red area, then you need to design a compensator that causes the poles when the loop is closed to move into the left hand plane. Now in the old days, when people were drawing maps of the world and there were places that were scary or unknown, they painted dragons on them. So let's think of the right hand plane as where there be dragons. We don't want to be there. The vertical axis is also an interesting place. Any pole that's on the imaginary axis is quasi-stable. That is, it results in oscillation. The oscillation doesn't increase in magnitude, it doesn't decrease in magnitude. It's undamped, it maintains its amplitude. Probably not a particularly useful place to put a pole either. There are a lot of natural systems, harmonic systems, you think of a mass on a spring, a pendulum or something like that, they generally have their planned poles are on this imaginary axis. So it's characteristic of an oscillatory system. The left-hand plane, shown here in blue, is where poles are stable. So that means that over time they will converge on zero. So if there's any energy in the system, it will be dissipated, the system will be stable. And this is where we want to place any poles of our closed loop system. The real axis is a little special in that poles that are there are non-oscillatory. They exhibit purely exponential decay. So important elements of the S-plane: the right-hand plane where there are dragons, where you don't want to be; the left-hand plane where things are stable. We have the imaginary axis itself, the vertical axis, and we have the negative real axis. If we look at the S-plane and we're interested in characteristics like the natural frequency of the poles, the natural frequency of the poles increases with our distance from the origin. So typically with the S-plane, we can display circles, and the radius of these circles is constant natural frequency. So any point that lies on a circle has got the same natural frequency. But what changes is the damping factor. So as we move from the imaginary axis around to the left and down, the damping of the system increases. So those radial lines are lines of constant damping. Typically we want to put poles in areas something like this. We want them to be reasonably well damped. We want them to be reasonably fast. We don't want to make them too fast, because if we try and make a plant move much faster than it is naturally able to move, then this will result in very, very large inputs to the plant in order to get it to move very, very quickly. So there's a sweet spot where we can have reasonable inputs to the plant. The system will settle quickly. That's a characteristic of its natural frequency, and the overshoot will be desirable, and that's a characteristic of damping ratio. So now we're going to consider two planes. We're going to consider the S-plane, which we are familiar with and just discussed, and a new plane, the Z-plane. And what we're going to do is to map an arbitrary point in the S-plane, multiply it by the sampling interval capital T, pump it through the exponential, and we will have the corresponding coordinate on the Z-plane. So this is a mapping or a morphing from one plane to another. So first of all, we're going to consider this blue band here. And this blue band in the S-plane is infinitely wide. It goes from the imaginary axis all the way out to the left, out to negative infinity. So that band with infinite area is mapped to the inside of a unit circle on the Z-plane. Now the vertical extent of that band on the S-plane is defined by the sampling interval capital T. So you can see that the top of the band is a J, because it's an imaginary number multiplied by pi divided by capital T. So that is a part of the stable area on the S-plane is mapped into the center of a unit circle on the Z-plane. The imaginary axis is mapped to the outside of that circle. And imagine the imaginary axis is infinitely long. It's mapped to a circle which has got a finite circumference. This area, the positive real axis, where there are unstable poles clearly, is mapped to the positive real axis on the z-plane, but it starts at 1 rather than starting at 0 as it does on the s-plane. It's offset by 1. The negative real axis, which is infinitely long because it goes from negative infinity to 0, maps to the interval 0 to 1. And this region, the bounds of the band in the s-plane, two infinitely long lines, are mapped to one finite line segment on the z-plane. Now, a really interesting and useful landmark is the origin on the s-plane. The origin on the s-plane, that's where a system that's a pure integrator has its pole. It maps to the coordinate 1, 0 on the z-plane, right? So it's at 1 on the x-axis on the z-plane. Now, as before with the s-plane, there's a region of dragons, so any pole that's outside the unit circle is going to be unstable, and we'll talk in a little while about how we determine the stability of a discrete time system. But if you're doing design, what you're trying to do is to keep the poles inside the unit circle. So let's look again at this z-plane, and we're going to overlay on that some lines of damping factor and frequency, and we can see that the frequency lines 0.1 pi on t, 0.2 pi on t increase as we move from the right to the left hand side of this unit circle, and we can see that the damping is very low near the edge of the circle, and it increases as we move down towards the horizontal axis. The damping numbers there are 0.1, 0.2, 0.3 and so on. Now, we mentioned before that the point that is at 1 on the real axis corresponds to an integrator. So if we look up the z transform of an integrator 1 on s, that gives us the transfer function in the z domain of z over z minus 1. The pole of that system, that's when z minus 1 equals 0, is when z equals 1. So that point, the rightmost black dot that I've drawn, corresponds to an integrator. It's a really useful landmark, useful thing to keep in mind when you think about the z-plane in an intuitive way. Now, the point at the origin on the z-plane that I've also marked is pretty interesting. It corresponds to z to the minus 1. It corresponds to a delay of 1 time step. Now, we can't represent a delay of any sort in the s-plane. This point at the origin of the z-plane doesn't really exist in the s-plane, but it does exist in the z-plane. And we can think of z to the minus 1, we can express that as the system on 1 over z minus 0, and we can see that that corresponds to a pole when z equals 0. So a delay of 1 time step introduces a pole at the origin on the z-plane. 2 delays introduces 2 poles at the origin on the z-plane. So let's think about it in intuitive or conceptual terms. A pole at the origin is a delay. A pole at z equals 1 corresponds to an integrator. I mentioned before about stability. Let's consider a pole on the z-plane at the location lambda. Now, lambda can be a complex number or it can be a real number. So what we'll do is we'll create a simple first order system, and we describe it here as z over z minus lambda. So this system has got a pole at z equals lambda, exactly the specification that I gave up above. Now, the time domain solution for this z domain expression is the number sequence gk is equal to lambda to the k. So clearly, if lambda has got a magnitude bigger than 1, then at each time step it's going to get bigger and bigger and bigger. It will be unstable. Whereas if lambda, the magnitude of lambda is less than 1, then as I raise it to increasing powers of k, it's going to get smaller and smaller and smaller. So the stability bound here is that if the magnitude of the pole is less than 1, it will be stable. The magnitude of the pole is greater than 1, it will be unstable. So that's the importance of this unit circle boundary. If a pole has got a magnitude greater than 1, it's outside the unit circle, it will be unstable in the region where the dragons live. So back to the last tutorial. I asked you to convert this continuous time transfer function into the z domain using the very simple backward integration rule. So what we do is we substitute s equals 1 minus z to the minus 1 over delta t, do some arithmetic, and we get this expression here. So if you did this in the tute, you can check your answer. See if you agree with what I got. We can do the same thing in MATLAB. Or rather, we can express this transfer function in MATLAB. So what I've done here is use the MATLAB function tf, which is short for transfer function, and I have given it the transfer function. And in MATLAB, I have to express this as two polynomials, a numerator polynomial and a denominator polynomial. So the first argument in MATLAB is a vector 2, minus 1, and 0. And so that corresponds to the coefficients of z in the numerator. So we have 2, which is the coefficient of z squared. We have minus 1, which is the coefficient of z. And we have 0, which is the coefficient of z to the 0. There is no constant term here, right? So that coefficient is 0. In the denominator, it's a bit more straightforward. The coefficients of our polynomial, we can see, are 12, minus 7, and 1. And I bung them into a vector, into the second vector, which we pass to tf. The third argument to tf is the sampling interval, which for our tutorial problem was 1 second. If I do that, MATLAB returns me something like this. It's actually a transfer function object, and it displays it here using a bit of ASCII art, and we can see that it looks a rather poorly rendered version of the lovely equation that I've shown here. It also gives us some handy extra information. It tells us it's a discrete time transfer function, and it tells us the sample time is 1 second. So now that I've got this transfer function into MATLAB, I can ask for the root locus, and I can plot the poles and zeros. Now I've only asked for the root locus for a gain of 0, so that shows us only the open loop poles and zeros. And so here they are, and they make a bit of sense. We can see that there are 2 zeros. There's 1 0 at the origin, and that makes sense because if we factor the numerator, we can see that it's equal to z times 2z minus 1. The roots of that are clearly z equals 0 and z equals a half. So there are the 2 zeros at the origin at 0 and another one at 0.5. The denominator is a quadratic, and it's got 2 roots, and we can see them there at around about 0.3, 0.4 or something like that. So what I can do is quite quickly, once I get the transfer function into MATLAB, I can display the pole and zero configuration. And we can see that they're all within the unit circle, they're all stable. The other thing that I can do now that I have this in MATLAB is ask for the step response. So if this was a transfer function, I put in a unit step, this is what would come out. And so I passed that transfer function into the MATLAB function step, and I ask for just 8 time steps of solution. MATLAB will actually figure out how many time steps you need, but I ask for 8 anyway. And so we can see that it's jumped up, it's a little bit of overshoot, and then it's sunk down. So I put in a unit step, and what came out was a step of about 0.16 and a bit. So the step has been attenuated. The gain is clearly not equal to 1. It's got a little bit of overshoot. So once I get the transfer function to MATLAB, I can do useful things like plot the poles and zeros, look at the step response. And here we have a summary. Here is our original transfer function. Here's the substitution for backwards integration. There is the z-plane expression. There is the pole zero map, and there is a step function. So let's do this for the Tustin transform. Here is my solution for gz, and here is the pole zero map, and here is the step response. And you'll notice that they are quite different. This one's still got 2 zeros and 2 poles, but they are at quite different locations. The step response also is a different shape. And I'll summarize the root loci, and the step responses in a few slides' time. So, actually converting from the S domain to the Z domain can be done by MATLAB for the case of a Tustin transform. So here is the MATLAB code that you'd need to do that. What I've done is entered the continuous time transfer function, again in polynomial form. So we enter the numerator, which is the coefficients of the numerator polynomial are 1 and 1. The coefficients of the denominator polynomial I get by expanding out the brackets. So s plus 2 times s plus 3 is clearly s squared plus 5s plus 6. So I put those coefficients in as a vector to the function tf. Notice that this time I don't put the third argument in. I don't give a sample time. So that's a hint to MATLAB that this is a continuous time transfer function, which is displayed there underneath. So when I display this transfer function object from MATLAB, it's using S now instead of Z because it knows it's continuous time. Now what I can do is take this continuous time transfer function and pass it to a MATLAB function called C to D. It's continuous to discrete. So I pass in the transfer function for my continuous time system, I pass in the sample time, and I tell it the type of conversion that I want to do. And I want to do a Tustin transform. And bang, out comes the answer from MATLAB. We can see now that it's in the Z domain because it's put Z's in the polynomials, and it's told us that the sample time is 1 second. So here's MATLAB's go at the transformation from continuous to discrete using Tustin transform. And over on the right hand side is my solution. You see that it's actually pretty close. The only slight difference is that MATLAB has in the denominator a very small constant term. It's got 10 to the minus 17, which is close enough to 0. So this is a small numerical error that's occurred in MATLAB's numerical approach to this solution. Notice that in my symbolic version, there is no constant term. So if you set that constant term equal to 0 in MATLAB solution and multiply through by some constants, you will see this polynomial is the same as the one that I derived. Now, MATLAB can do quite a number of different types of conversions. It can do the Tustin transform. It can't do the simple backward integrator that I showed in the previous slides, but it can do the pole zero mapping and it can do the Z transform. So this is how you use MATLAB to convert continuous time to discrete. Here's the Z transform approach, or it's rather Z transform solution. The key here is to put it into partial fraction form, so split it up into two terms, look each of those up individually in the Z transform table, and then do some algebraic manipulation to get it all back together again. And the solution is shown down the bottom here, and we can look at the pole zero configuration and we can look at the step response. Once again, just as we've done before. Now we can do this conversion in MATLAB by taking our continuous time transfer function, pumping it through the function C to D, but this time we use the command impulse. Now, MATLAB used the word impulse because another characteristic of the Z transform is that it is impulse invariant. So the impulse response of the Z transform system is exactly the same as the impulse response of the S domain system. It's the only characteristic that's preserved by the Z transform is the impulse response. The step response will be different, but the impulse response is the same. So it's often referred to as the impulse invariant transformation. All of these things have many, many different names. So here's MATLAB's solution to that discretization. Down the bottom is the solution that I worked out. Finally, let's look at pole zero mapping. Our continuous time system at the top, it's got a 0 at -1, it's got poles at that should be -2 and -3. We put each of those through the exponential, so they map to poles and zeros at e to the -1, e to the -2, and e to the -3. I do a bit of simplification and I get this discrete time representation. Again, shown here is the pole zero configuration and the step response. What's interesting about this system is it's the only one with just a single zero. They all have two poles, and most of them have had two zeros. This one has only a single zero. Now, pole zero mapping we can do with MATLAB using the command matched. Here's the MATLAB solution, and there is my solution. So we discretized our continuous time system 4 different ways, and we got 4 very different answers. So here they are in transfer function form. They're almost all second order numerator over a second order denominator, except for the pole zero mapping, which has only a first order numerator. So the question is, why are there so many different answers? Which is the best way to do it? And the answer is, it actually doesn't matter all that much for most of the control design techniques that we will use. The best approach to use is the Z transform. It's probably the most correct, but the Tustin transform doesn't do a bad job, nor does the pole zero mapping. So if you had the choice and you got the time, do a Z transform. If you want to do a sort of a rough and ready approach to discrete time design, I would go for either the pole zero mapping or the Tustin transform. And we'll investigate some of these in tutorials and future lectures. So here's a summary of the pole zero configuration, and the order is from top left to bottom right. It is the backward integration, the Tustin transform, the Z transform, and the pole zero mapping. Interesting to note with the Z transform that there is almost a pole zero cancellation at the origin, which they cancel out, leaving effectively 1 pole and 1 zero. And let's look at the step responses, and we see here that they have actually got quite different steady state values. Some of them are around about 0.16 and a bit, some of them are a bit above 0.7, one of them is a bit below 0.7, and they have different amounts of overshoot. Now, this system has been sampled rather slowly. We can see that it's showing a peak in just 2 or 3 time steps. We'll talk in a future lecture about how we choose the sample rate, but generally good practice is that you have anywhere between 10 and 30 time steps in order to reach the peak in the time response of your system. So we could say here that our sample rate is certainly far too low. Right? We should be sampling much faster. And as we sample faster, the difference between these different types of discretizations will also become less. So this is a rather extreme example. So what do we notice here? We notice that there are different pole zero configurations, different shape step responses, and different DC gain. As I've mentioned, the best choice depends a little bit on circumstance. You've got the time, take the Z transform. Don't have quite so much time, you want to be quick and dirty, go pole zero mapping or go Tustin transform. The differences will become less as the sampling time becomes a bit faster. So let's investigate the DC gain issue. We noticed before that we put in a unit step, what comes out is not a step. Or it looks like a step, but it's not a unit step. Right? The response is generally less than 1 in the steady state. So how do we figure that out? Well, it's actually quite straightforward. If we consider the input to the system is u, and it's the unit step function, and we already worked out the Z transform for the unit step, it's Z over Z minus 1, we multiply that by the transfer function of our system in order to get the Z domain representation of the output, y of z. Now it's simply uz times gz. So that gives us the transfer function. The final value, the steady state value, is given by what's called the final value theorem. So this is the steady state value that the Z transform signal settles down to. So the value at infinity is equal to the limit as z approaches 1 of z minus 1 multiplied by the dynamics of the system that we're concerned with. So what I'm going to get you to do now is to consider or rather I want you to work out the value of the steady state response of this particular transfer function to a unit step. So I've shown how to work out the transfer function of the system driven by a unit step. I've given you the final value theorem. All you need to do is to bring those two things together and come up with a solution for what's the final value of this dynamic system driven by a unit step. I'll give you a few moments and I'll be back. All right, so y, the output of the system, is z over z minus 1, which is the input multiplied by the dynamics of the system. Now, the steady state value is given by the final value theorem, so that's this limit. So we pre-multiply that by z minus 1, and then we have yz. Now, happily, some things cancel here. The z minus 1s cancel out, and we are left with the limit as z approaches 1 of z multiplied by that expression to its right. And now we substitute 1 for z into that expression, and with a little bit of arithmetic, we end up with an answer of 1/6. Now, if we look at the MATLAB solution to this system, we see that it converges indeed to 1/6. So this is a way you can work out analytically with a bit of pencil and paper what's the steady state value of a dynamic system driven by an arbitrary input. Now, it's time to start to bring all this together into the control system context. We've started in quite an abstract way talking about number sequences, Fibbonaci numbers, about transformations from the S-plane to the Z-plane. What we want to do now is to bring all of this into the context of designing a control system, because that's what this unit is about. So let's look at a classical continuous time control system. We have a plant whose dynamics are given by G of S, and we've designed a compensator, D of S, so that this closed loop system is stable, so that its poles are at a good location in the S-plane, so we get adequate rise time and a good or desirable amount of overshoot. R of t is the reference, and that's what we want y of t to track. So the brackets t simply means that this is a continuous signal of time, a continuous function of time. E is the error between the plant output and the desired output, and U is the output of the compensator, which is the input to the plant. These are all continuous functions of time. So we're going to start to morph this diagram into a digital control system. So the first bit of the morphing we're going to do is we're going to introduce a sampler, and we're going to turn our compensator into a Z-domain compensator. So now D is a function of Z. And the first thing to notice, what's shown there in the blue box, is the sampler. And what the sampler does is takes a continuous signal, E, which is a function of t, into a sequence of numbers, EK. So this is what the sampler does. Every t seconds, it takes a snapshot of the continuous signal and outputs a single number. So the figure down in the bottom right shows this. The top graph shows a continuous function of time. Down the bottom, we see a sampled version of that. So a lot of the information has been removed. We have periodic snapshots of the value of the signal. We've converted them into a sequence of numbers. And why have we done that? It's because we've been talking for a few lectures now about number sequences, about difference equations, and about Z transforms. And all of these operate on a sequence of numbers rather than a continuously varying quantity. So the output of our compensator, the output of dz, is a sequence of numbers. It's UK. Now there's a problem with this because UK is just a sequence of numbers. Every t seconds it outputs a new number. But the numbers are not defined in between the sampling intervals. So we could think of it as a series of spikes, right, which is the output of the compensator. Now, we can't feed a sequence of spikes into the plant for a number of reasons, but the primary reason is that these spikes have actually got no energy. They're impulses. They have got zero width, but some amplitude. So there's a mismatch between a sequence of numbers and a continuous time plan. So the trick is to introduce a device called a zero-order hold. And what a zero-order hold does is it takes a sequence of numbers and maintains that value until the next sampling time. So in this case, we import a sequence of numbers represented graphically as a number of spikes, and the output of the zero-order hold is a signal which has got a continuous value over time. When I say continuous, I'm using that in a loose sort of way because the signal is discontinuous in terms of its derivatives, right? It's got very sharp vertical edges in it, but it is defined for all time, whereas the sequence of numbers is not defined for all time, it's only defined at certain times. So the zero-order hold maintains the signal level between the samples. And this is the important thing we need to introduce to build a bridge between our digital compensator and our continuous plant. So if we consider a digital to analog converter, it's a device you're probably familiar with, it performs two important functions. One is it converts a digital number to a voltage, but the other function is this zero-order hold characteristic. It holds the voltage between updates. So if you write a number to a digital to analog converter, it keeps outputting the specified voltage until you tell it to output a different voltage. So here what I'm showing in the graphs at the bottom is the red signal, which is the output of a digital to analog converter, and the blue signal, which is the continuous signal that it's trying to approximate. And the figure on the bottom right, we have a much shorter sampling time, and you can see that the error between the blue curve and the red curve is on average much, much less. This is again related to sampling time. If the step time is very big, then there's quite a lot of the time where the error between the red curve and the blue curve is high. Ideally, we want those two signals to be as close as possible. So a digital to analog converter, D to A converter, is useful when you're connecting a digital system to a plant with to an analog input. So a compensator with digital output connected to a plant with an analog input. But we also talked previously about how there are some plants which have actually got a digital input. For instance, a pulse width modulated signal which is driving a motor. Well, again, we still have a zero-order hold function. So what I've shown here is the pulse width modulation signal in blue, and that's generally a very high frequency waveform, many, many kilohertz, which chop the current going to the motor to give an approximation of a variable voltage. But typically what we do is we hold the pulse width modulation duty cycle constant for the control period, which is shown here in T. So even in the case of a system with a digital input, we still have the zero-order hold function, which is holding the input constant over a sample time. So here is the system with our digital compensator, the zero-order hold in the plant. Now, the complication here is that the zero-order hold has actually got some quite interesting dynamics. And so our compensator now has to compensate not just for the plant, but also for the zero-order hold. So we need to combine the dynamics of zero-order hold with the dynamics of the plant to get, if you like, a modified plant dynamics. And then we design the compensator for those modified dynamics. So what are the dynamics of the zero-order hold? Well, it's a rather unusual expression. It's 1 minus e to the minus st all over s. Now we can compute the Z transform of a system, a continuous system GS, which has got a zero-order hold in front of it. And we do that by computing the Z transform of the product of the zero-order holds transfer function and the plant's transfer function. And we do a bit of arithmetic here. We split that into two parts. We take the Z transform independently of the two parts. And we utilize one of the properties of the Z transform that we talked about a lecture ago, and that is the so-called shift property. So we can take e to the minus st from inside the z transform, we can take it out where it turns into z to the minus 1. Then we can recombine these and we see that we've got 1 minus z to the minus 1 out the front of the z transform of our plant divided by s. So this is how we do the z transform of a plant with a zero order hold in front of it. So let's do an example. Consider this particular plant, very simple, first order plant with a zero order hold in front of it. So what we want to do is to solve this z transform and to the solution. So we have written down the appropriate z transform that we require. So it's got the plant dynamics and the zero order hold dynamics in there. The simplification from a couple of slides ago, and we have to then look up 1 on s plus a in our table of z transforms. It looks something like this. We have changed 1 minus z to the minus 1, multiplied top and bottom of that by z to get z minus 1 on z, do a little bit of simplification, and we end up with a result that looks just like this. It has got a single pole and it's maybe a gain factor that compared to the original plant in the S domain. So we can do this in MATLAB. Here is our continuous time transfer function, 1 over s plus a half. And we put that into the MATLAB function, continuous to discrete, ask for a 1 second sample time. And we give it the command ZOH, which is saying do the discretization but include a zero order hold in it. And MATLAB cranks out the answer, which is shown here, which is very similar to the answer that I have derived analytically. So let's do a quick recap of the S and Z planes. We talked earlier about the S plane, natural frequency increases to the left, damping factor increases as you move towards the real axis. On the Z plane, the directions are shown here. Natural frequency increases along somewhat strange shaped lines as you move to the left, and the lines of constant damping factor are also rather strange shaped. You can generate this figure on the right hand side using the MATLAB function zgrid, and the function on the other side you can generate using the MATLAB function called sgrid, and it will just draw this graphic showing you the lines of constant natural frequency and constant damping factor. Now let's take another example. Let's take a system with an integrator, a pole at the origin and a pole at 0.5, at minus 0.5, sorry, on the S-plane. And we're going to discretize this using MATLAB. We're going to do it correctly and introduce the zero order hold. And MATLAB tells us that this is the discrete time transfer function for this, equivalent to this continuous time plant. Now I can ask for a root locus of this discrete time system, and here is a discrete time or z-plane root locus. So we can see a couple of things. We can see that there is a pole at z equals 1 that corresponds to the integrator that I talked about earlier. We can see another pole at around about a half, and that corresponds to the other pole of our continuous time system. And we can see a zero at maybe minus 0.8 or something like that. And this is referred to as a sampling zero. When we discretize a system, we tend to introduce a zero, and it's generally in that negative part of the real axis, somewhere between 0 and minus 1. It's a sampling zero. Now, if we do the root locus, so we look at what happens to these poles as we increase the loop gain, we see that the poles come together and then they move in a great big arc. They join the real axis. One goes off to meet the zero and the other one runs away to negative infinity. Now the rules for drawing root locus in the z-plane are exactly the same as the rules for drawing a root locus in the s-plane. So if you know those rules, it's very, very easy to sketch up a root locus on the z-plane. The only difference is that on the z-plane, the stability boundary is this unit circle. So we can see that these poles quite quickly, the closed loop poles, leave the unit circle and don't come back in again. One comes back in again, but the other one has run away to negative infinity. So if we were to design a closed-loop control system, we'd have to choose our gains so that the poles were in a good location, but within the unit circle. So let's zoom into the root locus, and we can see here the root locus in the region of where the poles, the closed-loop poles, are stable. And so we could choose a gain that would get us, say, a damping factor of 0.7, but the natural frequency would be really quite slow, only 0.1 pi over capital T. And we can work out what that is in terms of radians per second, what that corresponds to in terms of a rise time. But we can see that if we wanted to get onto a faster, a higher natural frequency, say 0.2 pi on capital T, so double the natural frequency, we could do that only with a damping ratio of about 0.2. So if we wanted to be faster, but maintain the same damping ratio, we can't do it just by using a gain term. We'd need to introduce some kind of compensator. So let's introduce a lead compensator, and the lead compensator introduces a pole and a zero, and they're shown here. And what that does is bends the root locus around, and I have chosen a particular gain value to give us closed loop poles as indicated by those squares. So we've now been able to obtain a closed loop system which is faster and also more damped than I was able to obtain without the compensator. So the lead compensator is pretty simple. It's z plus a over z, and I can rewrite that as 1 plus a times z to the minus 1. So that is the discrete time version of a lead compensator. And the particular parameters that I chose the a is equal to minus 0.46. So that puts the 0 at plus 0.46 on the real axis of the z-plane, and I chose a loop gain of 0.5 to give me those closed loop poles. All right, to do all this in MATLAB is pretty straightforward. Here I have discretized it, assuming that there is a zero order hold present, sample time of 1 second. I have passed the continuous time system generated by TF into the function c to d. You can see the discretization. I've also created a transfer function for my compensator, which you can see there. I've called that C for compensator. D is the discrete time version of my plant. Interestingly, in MATLAB, I can multiply two transfer functions together just by using the multiplication operator. So I write C times D, and that's going to multiply the compensator C times the discrete time representation of the plant D together to give me that rather complex transfer function. Now, that is the same actually as writing the MATLAB function series C comma D. So these are two ways that you can put two dynamic systems in cascade, in series. You can use the series function, or you can use the multiplication operator. I passed that C multiplied by D together. That's the open loop dynamics of a system. I pass that into the root locus function, and there you see the root locus that I plotted before. And I choose the gains to get the closed loop poles where I want them. If we look at the step response for our lead compensator, it looks something like this, and that's not a bad compromise. It rise time's about 6 samples, and the overshoots reasonable, maybe about 15% or so. Now, there is one really important aspect when you design a compensator, and that's what's called causality. A compensator must be able to be expressed in terms of past and current values of signals. It can't predict the future. So when you implement a compensator, you can't build a compensator that uses a future value of a signal. And a simple test for causality is to look at whether when you expand it all out, it is all written in terms of powers of z to the minus 1. Because remember that z to the minus 1 is a delayed version of a signal. So here I've expressed my compensator in terms of a polynomial in z to the minus 1. If the polynomial ended up with powers of z that were positive, that means that it's needing to reach into the future, and we can't implement that. A very simple test for causality is whether the order of the numerator is less than the order of the denominator. It must be the case in order for it to be causal. If the order of the numerator is greater than the order of the denominator, it's not causal, it cannot be implemented. So, a summary of all the things we've covered in this lecture. We derived the Z transform for a number of useful cases. The unit step and the exponential, and in your exercise you developed the ramp function. We reviewed some important features, landmarks if you like, of the S-plane, and we mapped the S-plane to the Z-plane. So the S-plane is, the useful region of the S-plane is mapped to the inside of a unit circle on the Z-plane. We worked out how to determine the steady state response of a system to a unit step. We introduced the zero order hold, which is important when we connect a digital compensator to a continuous time plant. And we applied our knowledge of root locus design to the Z-plane. So we designed a simple compensator, we looked at the root locus, and we looked at the step response. Thank you very much for your attention. In the next lecture, we're going to move from transfer function land into state space land, and look at how we apply all of these techniques in state space, and look at how to design discrete time controllers in state space.